So far, we have looked at the discrete time Fourier transform as well as the discrete Fourier transform, and we looked at how these two transforms relate. So in this third video, we'll look at something called the fast Fourier transform. So even if the name fast Fourier transform has transform in the title, it isn't actually yet another transform, but rather it's just a fast way of computing the discrete Fourier transform. So before introducing the fast Fourier transform, let's first consider the discrete Fourier transform and what's involved in computing the discrete Fourier transform. So in the discrete Fourier transform, each of the transform coefficients, capital X of k, involves evaluating a sum of signal samples multiplied by complex exponentials. So for each of the values x of k, we have capital N multiplications to compute. And since there are capital N values of x of k that we need to obtain in order to obtain the full transform, the total number of complex valued multiplications that we need to perform is n squared. And similarly with additions. So if we wanted to evaluate this sum as a running cumulative sum, we have to add n minus 1 values. And this has to be done for all of the n components x of k, which means that the total number of additions will be n times n minus 1. So overall, both in terms of multiplication as well as in terms of complex additions, we can see that the complexity is of the order n squared. So if n is getting larger, so if we collect more signal samples, this may be prohibitive. So luckily there is a better way of computing the DFT which doesn't take quite as much time in terms of multiplications and additions. So there is an algorithm which runs in n log n time, and this is the fast Fourier transform. So the fast Fourier transform was popularized in 1965 in a paper by Cooley and Tuckey. So the ideas underlying the fast Fourier transform date back all the way to Gauss in the 1800s, but Cooley and Tuckey are generally viewed as the inventors of the FFT. And this said, there is also many different FFT algorithms available now, but the one that we will primarily discuss and consider in this course will be the radix 2 Cooley-Tuckey FFT algorithm. So whenever we just say FFT algorithm, this is explicitly the algorithm that we will be referring to. So to introduce the FFT, it's convenient to write the discrete Fourier transform using this W of n coefficient, which was equal to the nth root of unity. So using this, we can write the DFT as x of k being equal to this sum, where we have replaced the complex exponential by W of n, which is simply defined as the base of this complex exponential. So there is a number of properties for these W of n coefficients that we can prove and that will help us in deriving the FFT. So one of them that we have seen before is the property of periodicity. So W of n will, in terms of its power, be periodic with a period of n. So if we add capital N to the power of W of n, that's equivalent to not adding anything at all. And this is what we saw before, and which implied the periodicity of the DFT in the first place. A similar property will be a symmetry property, that if we don't add capital N, but instead add n over 2 to the power of the coefficient, what we will obtain is the negative value of the coefficient at this power k. There is a third scaling property which says that if we take this W of n coefficient to the power of 2k, that's equivalent to taking the nth over 2th coefficient, so W of n over 2, raising it to the power k. And all of these properties are easily verified by just considering the definition of these W of n coefficients. So we'll begin our derivation of the FFT by taking this sum to be computed and splitting it into two partial sums. One sum over the even values of n and one sum over the odd values of n. And these two partial sums together will of course make up the total sum that is evaluated in the DFT. So in order to parameterize and explicitly express the even and odd terms, for the even terms we introduce this dummy variable m, which runs between 0 and capital N over 2 minus 1. So for capital N over 2 terms. And wherever n appears, we introduce 2m as a parameterization of the even n. We do the same thing for the odd terms, but we replace each occurrence of n with 2m plus 1 here and here. If we now introduce the notation, so we give the even terms of the original sequence x a name, xe, and we give the odd terms the name xo, we can write it as follows. So we have the partial sum over the even terms and the partial sum over the odd terms, where we now have extracted the part of the exponential that doesn't explicitly depend on m. And the whole point of doing so is that we can recognize what these two partial sums are. So this partial sum is nothing more than an n over 2 point DFT of the even terms. And this odd term sum here is also a DFT, but in this case of the odd terms of x of n. And also in this case it's an n over 2 point DFT. So to summarize this, if we start with an n point sequence x of n, where n is even in order for this to work, and then we build xe of n and xo of n by taking the even terms of x of n and the odd terms of x of n to form these two n over 2 point sequences. And then we let x of k be the n point discrete Fourier transform of the original sequence x of n. And similarly we let a capital X of e of k and capital XO of k be these n over 2 point DFTs that we would obtain by computing the DFT of the even sequence and of the odd sequence. Then what we just saw in the previous slide was that x of k, the DFT for x, can be written as the DFT of the odd terms times this complex exponential, or this parameter Wn of k, times the DFT of the odd terms. And now we see that in order to define the whole DFT of x of n, k here has to run from, over the indices 0 to n minus 1. But since these are n over 2 point DFTs, we know by the property of the DFTs that these two sequences, xe of k and xo of k, need to be periodic with a period of n over 2. So whenever we run outside of the values from 0 to n over 2 minus 1, each of these terms will start repeating its values. And we can use that in order to arrive at a more computationally efficient way of obtaining x of k. So the way to do that would be to, for the first half values of k, just evaluate this formula. But for the second half of the values, we can just again read off the values of xe, and this particular multiplication that we have here we can obtain by noticing this symmetry property of these coefficients times the fact that we have already read out these values. So what we would do is would simply take a value from the previous evaluation, and instead of adding that, we would subtract it. So let's consider the number of complex valued multiplications that would be required in order to follow the previous derivation in order to compute the DFT of x of n. So the ingredients that we had was xe of k, which is a DFT of the even terms, and we have xo of k, which is a DFT of the odd terms. And since both of these are n over 2 point DFTs, we would need n over 2 squared complex valued multiplications in order to compute them, if they were computed in the straightforward fashion that we saw previously. And then we see that if we have xe of k and xo of k, we can combine these to get x of k. And what that would require is multiplying each of the odd terms with this complex exponential, and then adding or subtracting the terms together to get x of k. And in total, that would require n over 2 complex valued multiplications. So summing this up would give us 2 times n over 2 squared, which is the complexity of computing the two DFTs, plus n over 2, which is the number of multiplications required to combine these two DFTs in order to get the DFT of the sequence that we're after. And simplifying that would lead to n times n plus 1 over 2 complex valued multiplications in total. And it's quite simple to see that this would be strictly lower than n squared for all even values of capital N. So what this implies is that if we first compute the DFT of the even terms, and then we compute the DFT of the odd terms, and combine them using the previous derivation, then we will actually have to spend a lower number of complex multiplication than if we had computed x of k directly based on the definition of the discrete Fourier transform. So if we look at an example where capital N is equal to 8, so we have 8 terms to compute in the DFT, we could illustrate all of this graphically. So we have a sequence or a DFT of length 4 containing the DFT of the even terms, and we have a DFT of length 4 for the odd terms. And the odd terms get multiplied by these weights and then either added to the corresponding even terms or subtracted from them, which is what we obtain from this symmetry property. Now, the key realization behind the DFT is that if we can do this, if we can take an 8-point DFT and we can break it down into two 4-point DFTs and combine them with weights, then it stands to reason that we can take each of these 4-point DFTs and further break that down also as well into two 2-point DFTs. And we could illustrate that by adding a layer to this graph. So each of the two DFTs that we obtained in order to compute the final DFT, they don't need to be computed using the direct formula, but instead they can be computed using exactly the same trick by taking two 2-point DFTs. So in the case of the even terms here, we would take the even of the even terms and the odd of the even terms as the two components, and we would take the even of the odd terms and the odd of the odd terms and combine these using suitable weights in order to get the DFT of the odd terms in the original sequence. So if we can take a 4-point DFT and break it down into two 2-point DFTs, we could take a 2-point DFTs and break it down, adding another layer into two 1-point DFTs that would be combined using weights in a similar way as we've seen before. So for an 8-point DFT, instead of computing the two corresponding 4-point DFTs using direct formulation, we would add layer upon layer until we have reached the point where what we need to compute are 1-point DFTs. And a 1-point DFT is nothing more than a signal sample itself. So by doing this, we have created now a graph containing multiplications with complex weights, as here, followed by additions and subtractions in a number of layers, which will subsequently lead to full computation of the sought discrete Fourier transform. Multiplications are generally more demanding to evaluate in hardware than additions and subtractions. So when considering the complexity of DSP algorithms, it's quite common to just consider the complex valued multiplications and neglect the number of additions and subtractions. So to this end, let's look at the complexity of the FFT algorithm for a slightly more general version of the previous example. So we'll look at x of n and assume that this is a sequence of length 2 to the power of p, where p is an integer. So this means that the sequence x of n can be divided in the number of steps in order to arrive at 1-point sequences that we need to start with. Now the question is, how many complex valued multiplications over the whole process would be required to use the previous recursive procedure for computing the DFT of this sequence x of n? Would it be n squared? Would it be n times n plus 1 over 2? Would it be n times log 2 of n? Or would it be n over 2 times log 2 of n? The correct answer is n over 2 log 2 of n, so option number 4. And to see this, if we have a sequence of length n, which is equal to 2 to the p, where p is an integer, the number of stages, or the number of divisions of x of n in order to arrive at the 1-point sequences would be p, or equal to log 2 of n. And there would be n over 2 complex valued multiplications per stage. The way to see this is to see that overall there are n values which get propagated from one stage to the next. However, only half of those values get multiplied by these complex exponentials, so there would be n over 2 complex valued multiplications per stage. So the total number of multiplications would thus be n over 2 times log 2 of n. If we now turn the attention to the number of additions and subtractions, we see that there is a total of n additions and subtractions per stage. So the total number of additions and subtractions would be n times log 2 of n. So this allows us to summarize the FFT complexity, or the complexity of the recursive way of computing the DFT that we have just derived. So overall, we see that we have n over 2 times log 2 of n complex valued multiplications. We have n times log 2 of n additions and subtractions. So we can say that the overall complexity of the algorithm is n log n, either if you consider complex valued multiplications or additions, or the sum of the two. Now that we have obtained the overall complexity of the FFT algorithm, we can see that we can decrease it even further by identifying trivial multiplications. So in some cases, the weights that we multiply with are these roots of unity to the power of 0, which evaluates to 1. So multiplication with 1, for instance, is of course identical to not performing the multiplication at all. So we could remove all of these multiplications from the schematic, in this case for this example of the 8-point DFT, without actually changing the algorithm itself. There are also other multiplications, like this multiplication with a negative imaginary number that would be performed here. So we could implement that in hardware as simply an interchange of the real and imaginary part of the number that we're working with, along with the sign flip. And that actually doesn't have to take all of the hardware that the full multiplication would take. So in this particular case of the 8-point DFT, there are actually only two multiplications, this one and this one, that would have to be carried out in full. However, the number of multiplications that we could remove this way is decreasing relatively to the total number of multiplications. So the total number of multiplications of the algorithm would still grow like n log n if you look at the order for increasing capital N or increasing FFT sizes. Another note to make is that all of the operations within the FFT algorithm are of this butterfly type. So we typically take two numbers, we multiply one of the numbers, in this case lowercase b, with a complex weight, we add them together and we take the difference. So the thing to note here is that as soon as we've computed uppercase a and b in this operation, we no longer have any need for lowercase a and b in the algorithm. So what this means is that we could store a and b in memory previously occupied by lowercase a and b. So this is called implementing the FFT algorithm in place. So the only memory that we would need in order to implement the algorithm would be this memory required to store the original sequence, and we could replace that memory by the FFT of that sequence. In the beginning of the video, I said there are many different types of FFT algorithms, and so far we've only considered the so-called radix 2 FFT algorithm. And we derived that by taking the DFT sum in the definition and splitting it into two partial sums, one over the even terms and one over the odd terms. We could in principle do the same by splitting the sum in more parts. So if we have a sequence x of n that has a length which is an integer power of 3, we could take the DFT and its sum and divide it into 3 equal parts. And that would in the end lead to the so-called radix 3 FFT algorithm, which would work the same way. However, the question is now, what would be the complexity order of this FFT algorithm, of the radix 3 FFT algorithm? Would it still be order n log n, or would it be order n squared log n, or would it be order n log squared of n? Well, the answer is number 1, option number 1, so it would still be order n log n. And the way to see this would be similar as for the radix 2 algorithm. So we take this sequence x of n of length 3 to p, where p is an integer. We would divide it into stages. Each stage would have 3 equal groups, so they would be the log 3 or the 3 logarithm of n, which would be equal to p stages. Then we need to combine the result in each stage. And using a similar argument, we would see that you would have 2n over 3 number of multiplications per stage, and the number of additions and subtractions you would need would be equal to n. So the total number of multiplications would be 2n over 3 times log 3 of n, and the total number of additions would be n log 3 of n. So if we just look at the complexity order, that's equivalent to an order of n log n. So to summarize, the fast Fourier transform is an algorithm that can efficiently compute the DFT. It works by a sort of divide and conquer strategy, so it splits the DFT sums into equal parts and it combines these to build larger FFTs or larger DFTs from smaller DFTs. It reduces the overall complexity from an order n squared down to an order n log n, and for large n this is quite significant. There are many different versions of the FFT algorithm. All of them have a complexity order of n log n, and one can show that this is indeed the minimum complexity that you could possibly have for computing the DFT. We've looked at the radix 2 version of the FFT in more detail, and this is the most common of the algorithms. And as a side note, I should mention that you can also compute the inverse FFT or inverse DFT if you wish, by simply replacing all of the weights in the FFT algorithm by their conjugates and then dividing the final result by 1/n.